Okay, let's get started. Welcome you all to the live session 9. Here we will be solving some of the practice problem based on the video lectures of the week 9. So let's get started. Let's get started with the first problem. First of all, please try it by yourself. You can give your response in the chat box. After that, we will solve it together. Okay. So please first try it by yourself, and you can give your response in the chat box. Okay. Yes. Yes, all of you are correct. So let's let's try to see what has been asked in the question, and we will discuss it together. Okay. So here it has been asked, what is the mechanism of material removal in AJM? AJM, or uh, full form of AJM, is abrasive jet machining. Abrasive jet machining. So uh, first of all, I want to tell you what abrasive jet machining it is. It is a non-conventional machining technique. And if you would remember, what was the aim of the machining? Aim of the machining was to remove some material from the given component, and we have to achieve the some required shape along with correct dimension and good surface finish. So first of all, let's try to see how abrasive jet machining works. So suppose we have a piece which is here, and we want to remove some portion of material over here. So what we do in abrasive jet machining, we we had some abrasives. Actually, we have some small abrasive particles. Okay, and with this help of these abrasive particles, we try to remove the material. Earlier, we have already discussed there are uh, different other techniques of material removal using the abrasive particles, such as grinding. So in the grinding, what was happening there? Their abrasives were they were they were bonded to a wheel, and and early and in the earlier lecture we also have seen the buffing. So their abrasives were not bonded in the wheel, but they were used as a loose paste, and with the help of buffing cloth, we were trying to improve the surface finish. So likewise, that here we have abrasive particles. In earlier cases, the ab- abrasives in the grinding, let's say we talk about, let's say for the grinding or buffing, the aim was to get the final dimensional accuracy, or to get the good surface finish. But here the objective is little different. Ab- Abrasive jet machining, it is used to for some advanced materials. Basically, it is not used just only for the surface finish, or let's say uh, to achieve the good dimensional accuracy. It is important to machine those materials which are not which cannot be easily machined by conventional techniques. And abrasive jet machining, it is also used for to create some difficult shapes, which I will show in the video. But before that, let's quickly see its mechanism. So what we do here, we have collection of abrasive particles, and what we do, somehow we create a jet of these abrasive particles. So jet of abrasive particle means, so what we do, we take abrasive particles and we take some carrier medium. It may be air, it may be water. We take some carrier medium through which we try to increase the momentum of these small particles, and we try to increase its velocity, and we project them at the required location. So these small particles, so it is here, it is shown here. So suppose we want to machine this workpiece, we take abrasive, and these abrasive particles get mixed with the air, gas or air at very high speed. You can see this 200 meter per second. So because of high moving speed of air, the momentum of this abrasive also increases, and it comes and hits the workpiece surface. And when it hits the workpiece surface, so very localized deformation takes place. If the workpiece material is brittle, then because of high impact force, the material in very small area, they will get fractured, and fractured material is thrown away by the high speed air which is coming. And in this way, localized deformation takes place, localized brittle fractures takes place, and material gets removed with high jet of abrasive. So this is the mechanism. So now I will show you a video where you can see how abrasive jet abrasive water jet machining is useful to create some very difficult to make shapes. You can see here a jet of abrasive and water. It is coming and it is cutting the plate, which likewise there are some difficult to make shapes. You can see these. If you see this shape is not easy to make. You can see how it is making. So you can see this type of shape we can easily make. And now this is the final product. We don't have to go for the any kind of secondary machining. So so advantage is we can machine difficult to machine material, and um, we can create difficult contours, and the surface finish is also good, so that we don't have to go for any secondary machining. So these are the advantage of abrasive jet machining, and the mechanism is the first one, as you already told the correct answer. Material removal takes by brittle fracture due to impingement of fine abrasive particles. So let's move to the next problem. Please read the problem. First of all, please try it by yourself. After that, we will discuss it together, and you can give your response in the chat box. Okay, I have got one response. I'm waiting for this. Okay, let's start discussing it together. So this problem is also related to the uh, abrasive jet machining, and here it has been asked about the MRR, or material removal rate. So uh, with respect to the mixing ratio, so first of all, let's try to understand what is the mixing ratio. So as I told earlier, we had in abrasive jet machining, we have some abrasive particles, and we had some carrier medium. It may be air, it may be water, and we mix this abrasive along with carrier medium. This is abrasive mixing with carrier medium, and then uh, we create a jet of mixture of the previous one. A correct answer was this first one. Nagas Vildimas. The correct answer was A. Okay. Okay. So here in this second problem, uh, I was trying to explain what's the mixing ratio. So in abrasive jet machining, as I told, we have abrasive, we have a carrier medium, and we try to mix it up, and we try to create a jet of abrasive plus carrier medium, so that we could get the high we should get high momentum abrasive particles, so that they could hit the material and they could locally fracture the material. So what is the mixing ratio? Mixing ratio is nothing. Mixing ratio, or M. Mixing ratio, or M, it is nothing but volume flow rate of abrasive particles. Volume flow rate of abrasive particles divided by volume flow rate of carrier gas. Okay, or in short form we can write V dot G divided by V dot V dot A divided by V dot G. Okay, so now if we increase this mixing ratio, what what should be the behavior of the MRR, or material removal rate? So if you remember, what was the MRR? MRR is nothing but rate of material removal. And the aim of machining is to get higher MRR without compromising with the quality. So here also, what we can control, we can control this mixing ratio, and our aim is in such a way to mix the uh, amount of abrasive and carrier medium in such a way, so that we should get high material removal rate, and our uh, and the surface property should also not get distorted. So experimentally it has been observed this kind of relationship. If you try to plot the material removal rate versus the mixing ratio, so we get something like this. So here, if you just directly try to think, uh, material removal is happening because of the abrasive particles. So it is common sense, we can say, okay, if we keep on increasing the abrasive particles, then definitely more amount of material will get removed. But it doesn't happen. After a after a critical value of mixing ratio, if we further increase the volume of the abrasive particles, then MRR again starts decreasing. So can you think of why it is happening? Why it is happening? If you want, you can write in the chat box whatever we know from our knowledge. According to that, material since material removal is has been taking place because of the abrasive particles. If we keep on increasing the volume of the abrasive particles, then material removal should increase. But after some critical value, it starts decreasing. Can you think of why it is happening? You can unmute yourself. If some idea is coming to your mind, you can unmute yourself and you can tell me. Okay, nozzle wear. Suppose we have very strong nozzle, we have very hard nozzle, which is very difficult to wear off. Then also this kind of behavior will takes place. Still, this kind of curve we will get. So something else. So nozzle wear, uh, yes, it is correct. Nozzle wear will happen, but that is not true correct reason for reducing them. Uh, for reducing the material removal rate. Okay, I think Naga Srinivasi is in right direction. So let's let's slow down the process and let's try to see what is exactly happening. Okay, so now we have workpiece. Okay, and we have nozzle. Okay, so let's suppose first the case of uh, if we have less mixing ratio, what will happen? If we have, if, let's say here in this region, what will happen? So uh, I will draw. I Okay. So for first case, if mixing ratio is very less, then this is our nozzle, and this is if we have low mixing ratio, means this is low mixing ratio, and this is optimum mixing ratio. And this is, let's say, high mixing ratio. I told that the material removal will takes place with the help of abrasive particles, which they come and they impact the workpiece at high velocity. So if less mixing ratio will be there, then let then number of abrasive particles per unit time, number of abrasive particles hitting the workpiece per unit time, that will be less. So, and if mixing ratio is smaller, then the gap between two abrasive particles, it will also be higher. Okay, so let's say first abrasive comes and it removes some material. Then after first abrasive, second abrasive will come after some time, and again it will hit, then some material will get removed. So now in the case of low mixing ratio, the abrasive particles, they will come and they will hit and they will go away, but their rate will be very slow. In 1 second, very small amount of abrasive will come, and those small amount of abrasive particles are responsible for removal of material. So in this case, since a small amount of abrasives are available for material removal, therefore material removal rate will be slow. Now let's talk about what will be happening in the case of high mixing ratio. So again, we have nozzle and we have workpiece, and in high mixing ratio, what will be happening? There will be very large amount of abrasive grit particles that will be coming towards the workpiece per unit time. Okay. Now the distance between each abrasive particles is very small, and because of this, what will happen? Crowding will happen. Crowding means what? Suppose if first abrasive particles comes and hit the workpiece, so first abrasive particle will remove some material, but second abrasive particle will come, rather than hitting the workpiece, it will hit the abrasive particle, first abrasive particle itself, and that will not play any role in material removal. So now what will happen? Abrasive particles will collide within themselves rather than hitting the workpiece. More collision will be happening among themselves, and those collisions will not be responsible for the momentum transfer to the workpiece. Therefore they will not participate in material removal. Therefore, if the mixing ratio will be very high, the major portion of abrasive particle, they will not participate in material removal, therefore MRR will be less. Okay, so we it will be better if we would have some balance condition, so that so in balance conditions, what will happen? First abrasive will come, it will hit the workpiece and it will remove some amount of material. As soon as it will go away, Then next abrasive will come and it will again hit the workpiece and it will again remove the material. After just immediately uh, after when the second will go away, second abrasive will go away, it will followed by third, fourth, fifth. There will be only that much of abrasive. We will be mixing only that much of abrasive which will be actually responsible for the material removal, as well as there would be no lag, there will be no time lag as it was in the earlier case. The gap was too much. After first abrasive there was some lag, then again some next abrasive was coming, therefore the material removal rate was slow. So this is the optimum condition. Here the all almost major of major portion of the abrasive particles are participating in material removal, and that is the optimized conditions. Therefore the correct answer is it initially increases and decreases afterward. Okay, so if still any of you have any doubt, you can unmute yourself, you can ask me, or you can write in the chat box, and if it is clear then we will move to the next problem. Okay, so it seems there is no doubt. Let's move to the next problem. First of all, please try it by yourself. After that, we will discuss it together. And if you are finding any difficulty to understand the problem, you can ask me. Okay, I have got from Nagasilivas. Okay, I will wait for 1 more minute for others. Okay, uh, shall I start discussing, or I should wait for few some more time? Okay, so let's start discussing. Okay, so here what has been given during the abrasive jet machining, the mixing ratio used is 0.1. And after that, what we have to calculate? Calculate mass ratio if the ratio of density of abrasive and density of carrier gas is equal to 15. So let's start looking one by one. Okay, so what has been given? Mixing ratio. Mixing ratio is denoted by M, and what it is? It is the volume flow rate of abrasive divided by volume flow rate of gas. Okay, it is given 0.1. And what else is given? It has been given the density of the ratio of density of abrasive and density of carrier gas. So this ratio is given. So let's denote the density of abrasive by rho A and density of carrier gases by rho G. So this ratio is given as 15. And what has been asked? It has been asked calculate mass ratio. So similar to the mixing ratio, there is another ratio which is defined, and that is called the mass ratio. So mass ratio is defined as mass ratio. It is denoted by alpha, and it is given as the ratio of abrasive mass flow rate, abrasive mass flow rate divided by abrasive plus carrier gas. Carrier gas mass flow rate. Okay, so what alpha is? Alpha is nothing. If we write it in the short form, m dot a divided by m dot a plus m dot g. So m dot a is nothing but abrasive mass flow rate, and m dot g is the mass flow rate of the carrier gas. So now we have to calculate this ratio or alpha. And what is the abrasive mass flow rate? If we further try to uh, if further try to dissociate mass flow rate in the known terms, so what it will be? It will be nothing but density of abrasive particles multiplied by volume flow rate of abrasive particles. Okay, and similarly bottom also we can write like this. Here density of gas multiplied by volume flow rate of gas. Okay, now what we will do, we will divide the numerator and denominator by this term. Okay, what we will do, we will divide numerator and denominator by density of the carrier gas into volume flow rate of carrier gas. And if we will do it, what we will get? We'll get okay. Is it correct here? Yes. Okay. So we divided the numerator and denominator by this term, and we got this this quantity. And now, is it looking something known? Yes. Here it is the ratio of density of density of abrasive and the density of carrier gas, which is already here. And what it is also known. It is the volume flow rate of abrasive divided by volume flow rate of gas. So that is here. Okay. Now we will substitute the value directly from the top. And what we will get? We will get 15 multiplied by 0.1 divided by 15 multiplied by 0.1 plus 1. And if you solve it, what you will get? 1.5 divided by 2.5, which is nothing but 0.6. So alpha we will get 0.6, and the correct answer is A. Okay, so is it clear to everyone, or if there is some doubt? Shall I move to the next problem? Okay, let's move to the next problem. Please read the problem, and you can give your response in the chat box. Okay, I have got a response. I am waiting for others. So whatever comes to your mind, whatever according to you, whatever comes to your mind, you can please don't hesitate to give your response. Okay. Anyway, after that we will discuss it. Okay. 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 So let's start discussing. Okay. So it has been asked, which among the following is preferred material for nozzle in abrasive jet machining? So, as you know, in abrasive jet machining, what we were doing, we were having some abrasive particles, and we were trying to increase its momentum. Okay, and this high momentum abrasive is used for the machine the workpiece locally. Okay, so the main thing is the what we have high momentum, abrasives. Okay, so what we are doing, we were mixing it with some carrier medium. Okay, so let's try to see what is happening inside the nozzle. So inside the nozzle, we have um, we have abrasive particles, and we apply we have some mechanism or some system from which we create high velocity of the carrier medium. It may be water or it may be the air. If it is water, then we are producing the high velocity water jet, and if it is gas, we are using the high velocity gas by that is generated by compressor. And to in order to generate high velocity water jet, we have we are using the high pressure pump. And there again, if you remember, uh, your Bernoulli principle works. So oh, you have a pump, from there you generate high pressure of fluid, and then you convert this high pressure to high velocity. Okay, so let's not go there. So here we have, from there, let's say we are getting the high velocity water jet. Okay, and now we are mix we are adding abrasive particles. Okay, and what do you think during the mixing, what will happening? So when these abrasive particles, they will come into the high velocity of water jet, what will be happening? It will also get its velocity will also the velocity of abrasive particles will also increase, and same time it will also get mixed with the water jet. But how mixing will happen? It is not like water. It will not happen like something like this. Suppose this abrasive particles comes, it get mixed with the water, and directly it's coming to the bottom, or to the workpiece. It will not happen like that. It will happen, it will hit the water jet, and water jet will give a reaction force, and again it will hit the walls of the mixing chamber. And if you see the trajectory, exact trajectory of the abrasive jet particles, it will be happening something like that. It will hit, it will come and it will hit the water jet will give some reaction force, again it will go towards the mixing chamber, and some this kind of motion will takes place for the abrasive particles. And because of this, what will be happening, these abrasive particles will hit the walls of the nozzle many times, here. So multiple collisions of abrasive particles takes place with the nozzle. And if nozzle is not made up of hard material, what will happen? the wear of nozzle will takes place. So if the wear of nozzle will takes place, the water jet shape will change and we cannot get the focused water jet. If this geometry will get distorted, then water jet will diverge. And if it will diverge, then we will not get good surface finish, as well as the material removal rate will decrease. Okay, and we cannot machine very fine, uh, we cannot get the very fine cuts. Okay, so what we want nozzle material should be made up of very hard material, so that it should not get weared out with time. And therefore we are using a very hard material for the for making the nozzle. So what is the hardest material you can think of? Yes, please write in the chat box. If I am asking about to think of the hardest material, what it will be, which is available in our uh, earth, on our earth. So what is that material? Okay, someone have written tungsten. Apart from tungsten, yeah, tungsten is the one of the hardest, but not the, yes, diamond. Diamond is the hardest material which is known till date. Okay, but again, we cannot use diamond everywhere because it is very very costly. So we have to think of some affordable solution. No, graphite is very, it is not very hard. So if you have seen, graphite is used in your pencil which we use to writing. So how, yes, tungsten carbide is the harder, but it is not the hardest. So graphite is very soft. So uh, uh, basically graphite is nothing, it is, so here we have carbon, and this this has been stacked over layer by layer. Okay, and so if you see how graphite looks like, so we have carbon atom, and they have been stacked one over, they have been stacked like cards. Suppose we have cards, something like that, and they have been stacked. So we can easily slide them. Okay, if you slide, if you want to remove, if you want to deform it, you just quickly, if you put little force on any of this card, you can easily slide and you can easily get it deformed. If you can easily deform the material, then its hardness is very less. So if if you have, suppose if you have pencil, so okay, how do you write? We have pencil tip, and when we are writing, what we are doing, we are depositing the layer of graphite over the paper. So if we are writing, it means one layer of graphite has been deposited. Okay, and it can be done very easily because it is softer material. Whereas if you see the diamond, its shape is in 3D, or we can say sp3 bonding has been taken place. Whereas in case of graphite, if you see among the carbon, it is sp2 bonding is there, and these bonds are only in the plane, and each layer is in, they are joined by the some van der Waals forces. But if you see the diamond, it has strong 3D network of the carbon atoms, and which are, and therefore it is very hard because these bonds are very strong. So let's not go there. And just what I was trying to say, we are looking for the a nozzle material which is very hard. So let's try to see the hardness of all these materials. Okay, so here first one we have copper. So copper has hardness value of, so I am writing short form Cu. Okay, copper has hardness of 1.2. The scale is Morse. So there are many scales of measuring the hardness, but here just for the comparison purpose I am using Morse scale. Okay, so copper has hardness of 1.2, and after that what we have graphite. So graphite has hardness of, sorry, copper has a hardness of 3 on the Morse scale, whereas the graphite has 1.2. And after that sapphire. Sapphire is it is nothing, it is a type of alumina only, but it has very high hardness, that is hardness of Morse scale is 9. And after that what we have gold. Gold, it has Morse hardness of 2.5. So what we are looking for, we are looking for harder material which is suitable for the nozzle. So among these if we see, sapphire has the highest hardness value. So on the Morse scale, the hardness value of sapphire is 9, whereas if you see all other, they are very less. And diamond has the maximum hardness, that is 10. So it is the maximum on the Morse scale. So the correct answer for this problem is the sapphire. The nozzle material should be very hard so that uh, whenever the abrasive particles they hit the nozzle, the wear should not take place very quickly. Okay, so correct answer is sapphire. So is it clear to everyone, or any of you have any doubt? Okay, so if there is no doubt, let's move to the next problem. So till now we were solving the problem of abrasive jet machining. Now we will solve the problem on the ultrasonic machining process. So please read the problem. First of all, try it by yourself. After that, we will solve it together. Okay. Yes, I am waiting for your responses in the chat box. After that, we will discuss it together. Okay. Yes, I think, yeah, most of you are correct. So let's please start discussing the process of ultrasonic machining. Okay.
So ultrasonic machining, it is also called as the USM, and this is also a non-conventional machining technique. If I'm telling the word non-conventional, it means uh, this process is some advanced process, and this is used for the machining those materials which were which we were not able to machine by the conventional machining techniques. So let's first start, try to understand the process, okay, and then we will come to the problem. So this is the schematic of the ultrasonic machining process. So so here we have a workpiece, okay. So workpiece has been shown here, and we want to create some profile over the workpiece, okay. And here the process is a little different than older process till now what we have studied, okay. So here the process is like that, where we are using abrasive slurry. So abrasive slurry is nothing, it's a mixture of some fluid. It may be oil, it may be water. Mixture of oil or water with abrasive particles. So it is also abrasive based process, but here we are not using any high jet velocity or high momentum jet of abrasive particles. Here we are just having a mixture of abrasive and uh, water, that is called slurry. We have abrasive slurry. So we what we do, we submerge the workpiece inside the slurry, or we put the slurry over the workpiece, and what we do, we take a tool. So we take a tool in required shape. Suppose if we want to make hole inside the workpiece, then we take a tool with circular cross section, and if we want a square hole, we take the tool in the shape of square. So here we have tool. This is tool. And now this tool is attached with the tool holder, and this tool holder is something special. This tool holder is attached with some system which creates ultrasonic frequency. So what is the ultrasonic frequency? It is a very high frequency which we cannot hear by our ears. So these frequencies are 20 kilohertz or above, okay. So this much high frequency, so basically this tool holder is connected to with the transducer. So transducer is vibrating at which very high frequency, and since this tool holder is attached with the high frequency transducer, this tool holder is also vibrating, and therefore ultimately this vibration is get transferred to the tool also. So what is happening there? This is the zoomed figure. This is our workpiece, and over the workpiece we have slurry, which is the mixture of water plus abrasive particles. These are here, and this is the tool. And this tool, we are applying some load over this tool, some force, as well as we are vibrating it at very high frequency, okay. ultrasonic vibration. Ultrasonic vibration. So because of this vibration and this force, what will happen? This tool will come, this will hit the abrasive particles, and when it will hit the abrasive particles, this will this particle will get apply load over the workpiece. And if the workpiece material is not very ductile or it is brittle, then this abrasive particle locally fracture the workpiece material, and this material will get removed. And what and in order to remove the fractured material, we continuously keep on supplying the slurry. So continuous flow of slurry is required in order to wash away the removed material and to bring the fresh abrasive particles between the tool and the workpiece. So this is the mechanism of the material removal. So suppose if our workpiece material would not be a brittle material, then what would happen? So I will show you. Suppose we have a very tactile workpiece material. Okay, so abrasive particles will be here, and the tool will come and it will apply load over the abrasive particles. If workpiece material is not brittle, then because of this abrasive, the local fracture of material will not take place. Rather than plastic deformation of workpiece material will happen. But but we don't want plastic deformation. We want material to get removed. So if material is workpiece material is ductile, if it is ductile, so whatever force or whatever vibration we will give to the tool, that will create plastic deformation of the workpiece surface. The material, if workpiece material will not get fractured, then it will not get removed. So machining will not happen. Rather than localized plastic deformation will happen on the workpiece, and no machining will take place. Therefore, for the ultrasonic machining, we use it for the brittle materials. Okay, so this technique is mainly used for the difficult to machine material. Like suppose ceramic if we have ceramic material, then we cannot machine it by conventional techniques. Like suppose if we want to do milling, if we want to do create some uh, suppose if we have some ceramic, if we want to create a hole inside a ceramic plate, do you think with the milling cutter it is possible? Suppose this is the milling cutter, and if we try to make uh, make a some contour like this over the ceramic plate with, let's say it is HS tool or carbide tool, HHS or carbide, and this is, let's say, some very hard ceramic, or let's say alumina, or any hard ceramic, or let's say we have glass. So Do you think is it possible to make uh, do to remove the material by the milling process? It is not possible because the hardness of ceramic is very high than the HSS or carbide tool. So if tool is not harder than the workpiece, then it cannot remove the material from there. Okay. So this kind of, but here, the abrasive particles, they are very harder ceramics like silicon carbide or boron carbide B4C. So they are the harder particles than the workpiece. But since they are very brittle, therefore we cannot, therefore we have to remove the material in localized manner. Otherwise, if any impact load will come in brittle material, then if then a small crack will generate and it will lead to the complete failure of the material. Therefore, we are using abrasive particles so that only localized material removal should take place, and which will and gradually we will remove the material by small abrasive particles, and in this way there will be no formation of crack and the component will not get failed. So now let's come to the question. So it is important for the ultrasonic machining. The first option is for the tool. Till now I have discussed for the workpiece material and abrasive particles, but I haven't told anything about the tool. So if you see the mechanism, so we have workpiece, we have abrasive slurry over it, and we have tool. So I told that if the purpose of tool is to transfer the vibration and load from the transducer, so ultrasonic transducer. So this is the tool. The job of tool is to transfer the load and the vibration to the abrasive particles, and this abrasive particle will remove the material from the workpiece by small fracture. But what tool should be? What kind of tool it should be? This tool should be strong. Strong means it should have high strength. It should have high strength so that it could withstand with this force F. And this force is nothing. This is called a feeding force. Feed force. Okay. So this tool should be strong enough to bear the feed force. Same time, its life should be very long. It should not get weared out. And I told, if tool is made up of some ductile material, if it is made up of ductile material, then when then these abrasive particles, they will not able to machine the tool material. They will only locally deform the tool material. But this local deformation is not going to harm any, is not going to harm us. So if tool would also be very hard, then gradual wear will takes place, and as time passes, our size of tool will keeps on decreasing. So if tool is harder, then gradually tool itself get machined. Since tool is ductile material, therefore only local plastic deformation is happening, but machining of tool is not happening. Therefore tool is maintaining its shape. only localized changes is taking place. Therefore, we are looking for a tool which should be strong or tougher, and same time it should be tactile so that it should not get machined with the abrasive particles. So the first option is correct, and second is continuous flow of abrasive slurry is a must requirement. Yes, continuous abrasive slurry is needed to wash away the removed material as well as these abrasive particles. The abrasive particles which has been already used, they need to be taken away, as well as the material which has been removed from the workpiece, that is also needs to be washed away. For this purpose, we need to keep on supplying the slurry continuously. Okay, so the correct this statement is also correct. And the third one, the preferred workpiece in this case is the hard and the brittle material. Yes, this is this is the prime requirement. Otherwise, material removal will not take place. Only hard and brittle material can be machined by ultrasonic machining. So since all are correct, therefore the correct answer is D. So uh, I wanted to show some video, so you can quickly watch the video. Here we have the workpiece. So this is the abrasive slurry. Abrasive slurry is coming, and now this is the tool. It is vibrating, and you can see these are the shapes. There is a square shape tool. Okay, so after the machining, we have got these shapes, and they are very precise. Since only well localized deformation is happening, so the these holes or these are very precise. Okay, so for this problem, correct answer is D. So is it clear to everyone, or some more clarification is needed? Please let me know. If it is clear to everyone, shall I move to the next problem? Okay. Okay, so let's move to the next problem. Please read the problem and try to give your response in the chat box. Please read the problem and uh, you can give your response in the chat box. After that, we will discuss it together. Okay. I am waiting for response. Okay, so let me help you out a little bit. So in the ultrasonic machining, what I told, we want to machine a workpiece, and we do it here by the help of the ultrasonic vibrations, and we use abrasive slurry to for the machining purpose to remove the material. So uh, I just want to draw some schematics. So I will this is the tool. Okay, and here we have some workpiece. Okay, and we want to machine it, and we have abrasive grids. Okay, so now this tool will vibrate. We apply some force over it, feed force, and some vibration. We will give some vibration to this tool, and because of this machining will happen. Now uh, this is not a very simple process, this is little complex process. And uh, MC Saw, he was a scientist who has given a mathematical model for the material removal in the case of the ultrasonic machining. So according to his model, the this now I will little exaggerate this phenomena. So suppose this is a tool, this is the workpiece, and just for the uh, for understanding purpose, I am drawing abrasive particle. Okay, so MCSA first tried to uh, make some mathematical model assuming the shape of abrasive particle is more or less spherical. But when he did experiment, he found that his formula is not working, and when he tried to do experiment with the different sizes of the abrasives, he found that his formula was not working well. When he assumed the shape of abrasive was some spherical shaped, but then he took another assumption, so which was something like this: the shape of abrasive was not spherical, but it has some, it was something like this. He assumed a sphere where there are several spherical projections on the periphery of the sphere. Or if you see the overall shape of abrasive is, it is something like this. Rather than sphere, the shape of abrasive is something like this. And for the modeling purpose, he he, he has given the uh, he assumed the shape something like this. There is a sphere over which small spheres are projected. So the bigger sphere diameter he he has denoted by d, and the diameter of the small spheres he has denoted by d1. And there was a relation between this d and d1 that is given by mu d square. So this mu is a constant which is connecting between the this d1 and d. So based on that, he he assumed a model. So I will not explain the whole derivation, just I will try to show you what kind of configuration he is used in order to derive the complete material removal rate. So I am trying just schematic of it. Okay, this is tool. Now it is very exaggerated figure. Okay, this is workpiece, and this we called abrasive. Okay, so in the workpiece, what is happening? This abrasive is doing the brittle failures. It is brittle material. Okay, and this is ductile material. Tool is made up of ductile material, and this tool is some load is given and some vibration is ultrasonic vibration is giving the tool. So abrasive, what this abrasive is doing, this is fracturing the small piece of material on the workpiece, and this material is getting removed, whereas it is just only deforming the tool plastically locally. It is not able to remove the material from the tool. So, so this kind of deformation is happening. Okay, so if you little simplify it, so this one abrasive, this one abrasive particle, okay, it is it is indenting the tool material by a small amount. Let's call it ht, and this deformation, this this much of material it is removing in the in the hemispherical shape, and the depth of that hemisphere is given by hw. Okay, and this depth, the deformation ht and hw, this deformation is depends on the what is the flow stress of or the hardness of the material. Okay, so flow stress, if hardness is higher, flow stress will also be higher. Okay, so this ratio ht by hw, this is given by inverse of ratio of the flow stress, and this is denoted by lambda. Okay, and now I will show you his final form. So what I will do, I will add some new slide. So now I will show how his final formula or MRR. This is proportional to, there are some, this I am going to write some parameters, and then I will explain what are these. So this, so if you remember, T was what? It was the average diameter. Okay, if you remember this shape, so this was the D. So this is the average grain diameter. What is F? F is nothing but the feed force. And what is A? A is the amplitude of ultrasonic vibration. And what is C? C is nothing, it is the concentration of the slurry. Concentration means what? How much abrasive particles are present in the given volume. Okay, number of abrasive particles in given volume of the given fluid. Okay, it may be oil, it may be water. And what is the nu? Nu is the frequency of ultrasonic vibration. And sigma W, it is the flow stress of the workpiece material. So, and what is this lambda? This lambda is nothing, it is the ratio of flow stress of uh, workpiece material by flow, flow stress of tool material, that is lambda. So this process is uh, it depends on the many parameters. One is the grain diameter and feed force, amplitude of the vibration, concentration of the slurry, frequency of the ultrasonic vibration, and flow stress of workpiece material and the tool material. Therefore, it is a complex process, and how this formula has been come, that has been explained in the lecture. Okay, but for this problem, we just need to see this relationship and we can give the answer. So let's try to see what is the first option and what has been asked. Which of following is not true corresponding to the formulation of the material removal rate in USM? So first option is MRR is directly proportional to feed force to the power 0.75, or let's say 0.5 means 3 by 4. So let's say see the formula. This is the feed force. Yes, Amit, I will show to you later. In the last, I will show you all first, second, third slides. Okay. So uh, for this formula, if you see, the material removal rate is, here we have feed force to the power 3 by 4. So that is correct. Now next is MRR is inversely proportional to abrasive concentration to the power 0.75. So where is the concentration term? So concentration term is here. So if we see the material removal rate, it is directly proportional to the concentration to the power 1 by 4 or 0.5. So this option is not correct. Whereas if we see MRR is third option, MRR is directly proportional to amplitude to the power 3 by 4. Yes, it is correct. What happened? Yes, amplitude of vibration. Here we have amplitude of vibration. So it is directly proportional to the amplitude to the power of 3 by 4. So this is correct. So MRR is directly proportional to the frequency of the vibration. Yes, here we have frequency term. So MRR is directly proportional to the frequency. So statement wise, except B, all are correct. But correct answer is not true. So the correct answer is B. Okay. So uh, if it is if there is no doubt in this problem, we can move to the next problem. Or if you have some doubt in whatever I have explained, you can ask me. I haven't explained the derivation part, so it is little lengthy. So you can see on the lecture on the course lecture. But fundamentals I've explained. What assumptions are taken? What is the configuration which has been assumed in order to derive this relationship? So those things I've explained. Okay, is it clear? Okay, so let's move to the next problem. So if you find any difficulty, you can ask me later. Okay. So yes, this is the simple problem. Please think and try to keep his response in the chat box. After that, I will explain. Okay. Yes, I have got response from the. Okay. Yes. Yes, I think all of you are correct. So uh, for the ultrasonic machine, already I have explained. We are looking for uh, a workpiece material which is hard and brittle. We- and if the workpiece material is ductile, then we cannot remove the material, so only we will be deforming it plastically. So in this problem, we just try to find out which material is hard and brittle. So gold is a metal. It is very soft metal. And glass, yes, glass is not a metal. Uh, it is very brittle. So glass is very brittle. So we cannot uh, we cannot create we cannot do drilling process on a glass plate. So suppose we have glass plate like this, and if we take a HSS tool and if we try to make a hole there, what will happen? As soon as we apply the feed force over there, down feed, then some cracks will generate on the glass, and ultimately it will propagate, and this glass, this complete component will get fractured. So we cannot machine glass by conventional techniques. Therefore, we have to go for the advanced machining like the ultrasonic machining. Aluminum, it is a very soft material. It is also a metal, so it can easily be machined by HSS, or let's say carbide tool, or any tool. It is soft material. Steel is harder metal, so but it is not. It is also ductile. Even still, there are many categories: mild steel, high carbon steel, cast iron. So only I think the high carbon steel uh, and cast iron, these two are less ductile, but they are not completely brittle. So they can also be easily machined with the conventional techniques. So, but glass cannot be machined by the conventional technique at all. So yes, correct answer is glass. So let's move to the next problem. Please read the problem and uh, try to get the correct answer, and you can give your response in the chat box. You can give your answer in the chat box. After that, we will discuss it together. Yes, I have got only one response. I'm waiting for others. Okay. Okay, so let's try to find the correct answer together. So, what has been asked in the problem? If roughness of part surface obtained through the USM is reduced, so uh, what we have? So, suppose we have a workpiece, okay, something like this, and we have tried to uh, make a square hole over it, or let's say something like this. Okay, so we have made a hole something like this. Okay, so but right now, what is there after the ultrasonic machining? If we see the surface, then this is the machine surface. Okay, this is the machine surface. I will show in zoomed manner. So if you closely look it, then this kind of small asperities will be there, and because of this we will get some surface roughness. So peaks and valleys, small peaks and valleys is there. Because of these small peaks and valleys, we will get the roughness. And why these peaks and valleys we have got? Because Suppose this was the surface and we had a small abrasive over it. Okay, now we had tool, we applied some load over it and some vibrations, and what will happen, this abrasive will go and remove the material in nearby vicinity of, so this abrasive will remove material from here, this will remove here, this will remove here, likewise material will get removed. And after material removal, how it will look like, it will look like something like this. Wait, so it will look something like this. So whatever peaks and valleys we are getting over here, that will based on the what was the size of abrasive particles. Okay, if the abrasive particle size was bigger, then this deformation zone will also be bigger, and because of this bigger deformation we will get higher peaks and valleys and we will get higher roughness value. So if we want to improve the surface finish, then if we use some fine abrasive particles, something like this. Okay, okay, fine abrasives. Okay, when this tool will vibrate and it will apply load on this abrasive particle, then the formation zone will become very smaller, and from this small area fracture will take place and material will get removed, and finally we will get a surface which has very small asperities. Okay, and now if you check the surface roughness of this value, this is high surface roughness. Roughness is higher. Here we have very small surface roughness. Roughness will go down. So surface roughness is coming because of the what size of particles we are using. So if we use bigger size slurry particles, so then we will get higher roughness, and if we uh, use a smaller size of abrasive particles in the slurry, then we will get good surface finish or surface roughness value will be low. So correct answer for this problem is this one. Whereas if we see other options, like if we increase the slurry flow rate, then what will happen? So if we increase the slurry flow rate, then what will happen? So increasing slurry flow rate means this slurry, whatever slurry has been utilized, which has been already undergone for the material removal, they will washed away and they will get replaced by similar kind of slurry. Uh, they will be replaced by new abrasive particles, but their shape and size will be almost similar. So surface roughness wise, it will not create any difference. Whereas if you increase the flow rate, then it can affect the material removal rate, because new abrasive particle will have fresh cutting edges and they can remove the material faster. So if we increase the slurry flow rate, then it won't have any effect on the surface roughness value. Okay, and if we see the option number C, that is frequency of vibration. So if we increase the frequency of vibration, it means in 1 second, suppose we have abrasive particles and we have tool. and this is workpiece. So material was getting removed from the workpiece because of the vibration, because of the load which we have applied and this vibration. So suppose if we have low frequency, so if we are at low frequency, let's say 100 hertz for example, but in actual the frequency which we apply it is always greater than 20 kilohertz. For example, I am saying if we are using 100 hertz, it means the tool is vibrating 100 times in a second. If it is vibrating 100 times per second, it means the abrasive particles maximum which can undergo for the machining is 100 times in a second. So let's say it has removed 100 small layers in a second. But if we increase the frequency, what will happen? Let's say if we do it 200, then our tool will vibrate 200 times. And since it is vibrate 200 times, then it will remove 200 layers. But again, the roughness value of the machine surface with 100 hertz and with 200 hertz both will be same because the size of slurry particle was same. So if we talk about the third option, changing frequency is going to change the material removal rate, not the surface roughness value. So the correct answer is B. Only the size of abrasive particles is going to affect the surface roughness. Okay, is it clear? If you have any doubt, you can ask me. Okay, so we'll move to the last problem of the day, and please read the problem and try to give the correct answer in the chat box. After that, we will discuss it together. Okay, I have got only one response. I'm waiting for others. Okay, so uh, let's try to discuss it together. So in this problem, it has been asked in ultrasonic machining, the material removal rate it plotted as a function of feed force of the ultrasonic machine tool. With increasing the feed rate, the MRR exhibit following behavior. So okay, so I will show some graphical representation of these options. Okay, for option, so I will plot MRR on the y-axis and feed force, feeding force F. So here also MRR F. So first option is increases linearly, second option is decreases linearly, third option is does not change, fourth option is first increases then decreases. So same time I will also write the equation of the MC shock. So this relation, this is MRR, this is proportional to D f to the power 3 by 4. Okay, so if you see this relationship, what we find, we can find that the MRR, and there is a relation between MRR and the, this is the feed force. So at least one thing when we can say, there is a no linear relationship between the MRR and the feed force. So what we can say, Q is directly proportional to the feed force to the power 3 by 4. Okay, so if we increase the feed, then MRR should also increase. So but this relationship is not linear. Okay, so this option, first option, has gone. What about the second option? Second option is not right, because MRR should increase with increasing the feed force, and for the same reason third option is also not correct. So, and for fourth option I have drawn some curve, something like this, which is first increasing then decreasing. So if you see, just mathematically see this relationship, that MRR should increase by increasing the feed force with some function which has power 3 by 4. So there should be some non-linear curve. Okay, this curve is not linear. I should make it little more clear. This, okay, okay. So according to this relationship, this curve should be something like this. Okay, this curve is showing that Q is directly proportional, and Q is directly proportional to f to the power 3 by 4. So something this kind of curve is expected theoretically. Now let's try to see the process. So we have this tool, we have workpiece, and in between there are abrasives. Okay, what we are doing, we are applying some feed force over it, and we are giving some vibration to the tool. So as I told, because of this force and this vibration, these abrasives, they are going to deform the material in the air, and they are going to fracture the material in workpiece in nearby regions. Okay, so this should be there. So if we keep on increasing the force, of course the the fracture size will become larger. If we give high load, then fractured material will then workpiece will have higher area or higher fractured volume. So MRR should increase, but there is a limit for that. It is not like we can keep on increasing the load and we can continuously getting the higher MRR. Why? Because if we give very high load, then what will happen? A time will come when this abrasive particle itself get crashed. After certain value of its ultimate tensile strength, this this abrasive particle itself get fractured. Okay, so suppose this earlier this uh, abrasive particle was something like this, but when we applied high load, it itself get fractured. Then it will become hemisphere, something like this and something like this. If it will get fractured itself into small pieces, then what do you think? The the deformation area will become larger or smaller? It will become smaller. So till the till the if we keep on increasing the load till that abrasive particle is not getting fractured, then material removal rate will keep on increasing. But if we exceed the load in such that our abrasive particle itself get fractured or itself get crushed, then again material removal rate will start decreasing. Okay, so the correct answer is D. Okay, is it clear? Okay, so I have explained all problems for the today. If you have any doubt, you can ask me. Okay, if there is no doubt, then we will meet next Tuesday at the same timing with some problem based on the video lectures of the week 10. Okay, okay. So Hamid, I think you need some help regarding the problem number 1, 2, and 3. Okay, I think now you can take the screenshot. Actually, this is the video. The blue one is the video, so that is not required. That you can see later on the NPTEL website. Okay, first problem is over. Shall I move to the second? Shall I move to the third? Okay, thank you everyone. Okay, so so see you all next Tuesday at the same timing. Okay, till then, bye bye, good night.